In section 6.1, we're going to explain the basic behaviors of waves. We're going to describe the wave nature of light. We're going to learn some equations for relating frequency, wavelength, and energy of a wave. We're going to distinguish between line and continuous emission spectra. And then we're going to describe the particle nature of light. First off, what is electromagnetic energy? We've really been wondering this for a long time. Our very first ideas around this came from Isaac Newton, where he did some experiments and decided that white light consisted of individual colors of rainbows combined together. Anybody who has seen the classic experiment with like a prism, you shoot white light into it and you see a rainbow come out, you can see where he came up with this idea. And then he started to theorize that light was composed of streams of extremely tiny particles traveling at very high speeds. After that, we had some early experiments. Thomas Young started passing light through very narrow slits and noticing these interference patterns that was happening. This kind of made him kind of start to question Newton's ideas, because while we didn't have any good math to decide why these interference patterns would happen with particles, it does fit very nicely into the theory we had about waves and how they propagate. After that, James Maxwell, he started to theorize that what light was actually only a small part of a vast spectrum of electromagnetic waves, that we were only really looking at a small part of a greater whole. All of these observations started to lead to something we call the wave-particle duality of light, that it behaves both as a wave and a particle. We talked a little bit about interference patterns. I'm going to use some language that we haven't really defined yet, but I want you to get an idea of what this is. Interference patterns arise when light passes through these narrow slits. What can happen is that the peak from one wave corresponds with the trough of another. They cancel each other out and we get destructive interference. These are the darker parts of the interference pattern. Another option is that two troughs or two peaks come together and they add to each other. We get constructive interference and we actually wind up with a spot that's brighter than even the initial lights were. Again, these are only really explained by the wave properties of light. And here we can picture an interference pattern. One of the first things you might be questioning is, why do we even really care about this? And really, the interaction between light and matter is used a lot to really analyze matter and to learn more about it. A lot of analytical techniques are based on this. Here is a picture I think that really illustrates how we can do this. This is a picture of the Crab Nebula. And we actually know that the light emitted by this nebula is due to the elemental composition within the nebula. So sulfur cations produce those green filaments that you see, and the red filaments are produced by oxygen cations. So by analyzing the light coming off the nebula, we get an idea of what its elemental composition is. So let's jump into this. Waves. A wave is an oscillation or periodic movement that can transport energy from one point in space to another. We kind of have an idea of what a wave is. We've seen waves before, but this is really a little bit more of a generalized definition than maybe we're used to. We can think of waves as maybe like you play jump rope. You shake the end of the rope, you see it kind of propagate through the rope. You drop a pebble into a pond and waves ripple across the surface. And even ones that we experience but can't really see, like the expansion of air that accompanies lightning, that thunder, that is a wave that is propagating out from the lightning strike. But in any of these cases, kinetic energy is transferred through matter, whether it be the rope, the water, or the air, while the matter remains essentially in place. So the speed of light. So waves are not just restricted to matter. In our previous examples, we actually have electromagnetic waves. And these consist of an electric field oscillating in step with a perpendicular magnetic field, both of which are perpendicular to the direction of travel. That is a big statement that would be covered a little bit more in a Phys 2 course, electricity and magnetism. We're not really going to get into that too much here, but we're going to talk a little bit more about how electromagnetic waves interact with matter. And the real thing that you need to have is a takeaway that there is a set speed of light as it travels through a vacuum. All light, electromagnetic radiation, regardless of its other properties, is going to travel at 2.998 times 10 to the 8 meters per second through a vacuum. How do we characterize these waves? So we've talked about a spectrum. They're all different, right? So there's different points in this spectrum. How are we going to quantify that? Well, we have three descriptors right here. We have the wavelength. This is the distance between two consecutive peaks or troughs in a wave. We have the frequency. This is the number of successive wavelengths that pass a given point in a unit of time, because again, this is propagating. It's moving through some medium, right? And then we have the amplitude, 1/2 the distance between the peaks and the trough, or essentially how high are the waves. What are our units for frequency? Frequency is usually described using reciprocal seconds, per seconds, and this unit is called a hertz. So it's important for you guys to realize that when you see this Hz hertz, that unit is synonymous with 1/2. The hertz is a really small unit, so you'll often see it in pretty high multiples. So you have the megahertz, or 1 million hertz, or the gigahertz. 1 billion hertz are often used. So how can we relate these together? The product of a wave's wavelength and its frequency, which we're going to describe as lambda times nu, those are Greek letters, is the speed of the wave. So we have this relationship here where we have c, the speed of the wave, is always going to be equal to this constant and is equal to lambda times nu. Again, lambda is in units of meters and nu is in units of 1/seconds, and so we wind up getting this speed here of meters per second. Wavelength and frequency are inversely proportional, which means that as the wavelength increases, the frequency decreases, and vice versa. So let's see if we can kind of picture this a little bit. So here I have a distance traveled in 1 second. Okay, you can see here that a wavelength is from one peak to another. All right. So in this distance, we have traveled 1, 2, 3 wavelengths. So our frequency is 3 cycles per second, or 3 hertz. Here we are traveling 1, 2, 3, 4, 5, 6 wavelengths across in 1 second, and we now get 6 cycles per second, or 6 hertz. And you can see that as the frequency went up from 3 to 6, the wavelength went down. This wavelength would actually be half of what this wavelength, lambda 1, would be. And again, here we can see that after 12 cycles, the wavelength is even smaller, and we're getting through more and more of them in that 1 second time frame. Picturing amplitude, if you kind of thought of a line that went straight through the middle of this wave, the distance from that center point up to the highest peak or the lowest trough is going to be our amplitude. And here we have a lower amplitude. You can see that's kind of a squashed down wave. If the wave was even higher, we would have a higher amplitude. The electromagnetic spectrum is the range of all types of electromagnetic radiation. Visible light makes up only a small portion of that electromagnetic spectrum, and each of the various colors of visible light has a specific frequency and wavelength associated with it. So let's see if we can kind of picture that. So over here on the far left side of our electromagnetic spectrum, we have the highest frequency, lowest wavelength, highest energy types of electromagnetic radiation. That goes all the way up to gamma rays, which are very, very powerful rays. Some of our examples of that would be like cosmic rays. These are like cosmic radiation left over from the Great Big Bang Theory. The PET scan that's used in medicine uses gamma waves to essentially irradiate your insides to get images. Then we have X-rays. We're most familiar with these as a way of imaging bones, right? Because the X-rays can pass through our flesh, but they don't quite have the energy to pass through our bones, and we can do some imaging doing that. Then you have ultraviolet rays. These are used in a lot of things. Here they have the example of dental curing. There's also where they use ultraviolet radiation to cure like glues and plastics and stuff like that. And this is also the type of radiation that's going to give you like a sunburn from the sun. Then we have a very small portion here. It contains all of the visible light that we see. Okay. Then we have infrared radiation. We've used these for night vision and remotes and stuff. This radiation is most associated with like heat signatures and heat giving off infrared radiation. Then we start to get into microwave technologies, and these are used in things like wireless data signals, the data that goes to your phone and stuff, your cell phones, and they also power microwave ovens. And then we have this vast region of radio frequencies that are used to transmit both images and sound that we've been using for many, many years. So how do we interconvert between wavelength and frequency? We saw that they were related. We developed a thing. Let's do a little example here. We have a sodium street light that gives off yellow light that has a wavelength of 589 nanometers. What is the frequency of this light? So we rearranged the equation we had before to see that the frequency is going to be equal to the speed of the light divided by the wavelength. We know the speed of light. That's that 2.998 number. We have the wavelength in 589 nanometers. We do have our speed of light in units of meters per second, and we have this in nanometers. So we're going to have to make a conversion here. We need this to be in meters. So we make our conversion here, and we wind up getting 5.09 times 10 to the 14th reciprocal seconds. Here's an example where we can see that radio waves are everywhere, that we use them to send signals. These can be getting more and more sophisticated. We use them now for over-the-air TV broadcast. We use them for, more traditional things like ham radio, CB radio and stuff. But more and more, we're relying on this for data transmission and digital signals, like the new 5G that's coming out for your phone. How does it work? So, if this was the signal that I was trying to send, just this sine wave, right? I have two kinds of modulation that are typically used. You have AM, amplitude modulation, or you have FM, frequency modulation. So, how do these two work? So if I start off here and I say, okay, I want my signal to increase to here. In AM modulation, I'm going to make the amplitude go up. So the higher the amplitude, the higher this wave goes. The lower the wave goes, the lower the amplitude is going to go on my signal that I'm sending, until I can reconstruct this signal based on the amplitude. With frequency modulation, what I'm doing is changing the frequency. So as the signal goes up and I want to have a higher signal, I increase the frequency. As the signal goes down, I decrease the frequency and then back up again over here. Both of these have their upsides and downsides, and that's why we still have both AM and FM radio. So not all waves are traveling waves. Not all of them go anywhere. They don't move through the thing. These waves are known as standing waves. And standing waves, really, they play an important role in our understanding of electronic structure because they're the first time that you start to see quantization. And basically what happens is if you have a standing wave, the standing waves can't just be any number of waves between 2 points. It actually has to be what they call half integers, or n times 1/2 wavelengths between the two endpoints. So this only leads to discrete values that are possible. And we can even have a special case of the harmonic waves in which some points between the two endpoints are not in motion. These are known as nodes. And we're going to see a little later that at the quantum level, the very small level that atoms and electrons are working at, they also have quantized energies, and that these nodes start to appear in the way that electrons move. So let's see if we can picture this standing wave first. So I said that it was half integers of the wavelength. So if a wavelength is it going up and then back down again, we can see that this first top one here is actually only half a wavelength. So this is only a up and none of the down, right? Here we have 2 halves or 1 full wavelength. So we get the up, we get the down, it comes back to its first point, and in the center here we have this point that isn't moving. This is our node, right? While this is wiggling up and down, this guy stays stationary right there. Here we have 3 halves, so we're going to have 1/2 of a wavelength, the other half of a wavelength, and the third half of that wavelength. When we now have 2 nodes, and so on and so forth, each time adding a node and another half of a wavelength. This is not restricted to the one-dimensional example that we just had. This could also happen in 2 dimensions, or even we'll later see 3 dimensions. And one way of picturing that is to look at something that's like vibrating. So here they put like kind of gravel on top of these guys here, and then they wiggle it, and they can therefore create standing waves, which produce these patterns on the top with the gravel, where you can see those are where the nodes are forming. Black body radiation. So I'm going to mysteriously state that sunlight consists of a range of broadly distributed wavelengths that form a continuous spectrum. So we have a continuous spectrum coming from sunlight. A black body is a convenient, ideal emitter that approximates the behavior of many materials when heated. So if the sun is producing light from being heated, maybe we can kind of use the idea of the black body to model that. One good approximation of a black body that can be used to observe is the idea of like a metal oven. So what kind of electromagnetic radiation are we going to see when we heat up the inside of an oven? And then, so we have the problem with black body radiation, that we have something called the ultraviolet catastrophe. The maxima in the black body curves, lambda max, shift to shorter wavelengths as temperatures increase. theoretical expressions as functions of temperature fit the observed experimental blackbody curves at longer wavelengths, but there is a significant discrepancy at shorter wavelengths, and this became the ultraviolet catastrophe. So let's see if we can picture this. So what we can see here is that as the temperature of a blackbody goes up, the largest lambda max, where you're seeing the highest intensity of radiation, gets to be these shorter and shorter wavelengths, and it gets to be more and more intense, right? Where here it's producing visible light, here it's producing ultraviolet light, and here it's producing infrared light. Now, if we overlaid that, the temperature of with the black body, the temperature of the sun versus the sunlight, you see really good agreement for all of the infrared radiation and stuff. But then right here, even in the visible, it seems okay. But then you see this wild discrepancy right around where you start to move over to ultraviolet light, where it no longer appropriately models. The black body doesn't really fit the data we have for sunlight. So something is happening right here where we no longer have a good model for what exactly is happening within the sun using just the black body theorem. So what is that? Well, around 1900, Max Planck derived a theoretical expression for blackbody radiation that fit the experimental observations exactly. Planck developed his theoretical treatment on the premises that atoms are composing the oven vibrate. So he's thinking about vibrating atoms here. The atoms vibrated at increasing frequencies or decreasing wavelengths as the temperature increased. So what Planck did that was so revolutionary is that he started to develop a theory that related the energy of these vibrating atoms to the frequency. And he said that the energy has to be equal to n, where n is 1, 2, 3, or 4 or something, times some constant, which is known as his Planck constant now. You can see down here it's 6.626 times 10 to the negative 34 joule seconds. So you take joule seconds, you multiply it by reciprocal seconds, you get joules, which is the energy unit we've seen before. And the idea that it can only have these discrete values of 1 or 2 of times that, or 3 times that, or 4 times that, that is quantization that we saw before with the standing waves. So what exactly happened to cause this UV breakdown? Well, out here where we had higher wavelengths, lower frequencies, we have less energy, right? And everything behaves really, really nicely. Then all of a sudden we start to get into this visible UV radiation. And what's happening is the electromagnetic waves at this point now have enough energy to start doing different things. They now are able to excite electrons, to cause atoms to do things other than just vibrate. And that leads to this kind of erratic behavior around it as as more and more modes of energy transmission are possible. So thinking that the atoms are just vibrating isn't going to work for these higher energy electromagnetic waves. This enters into the photoelectric effect. And it had been observed that electrons could be ejected from the surface of metal when hit with the right kind of light. So the frequency of this light has to be large enough, therefore they have to have enough energy to eject these electrons. And what was surprising to them is that this didn't rely on the brightness of the light, but instead to its frequency of the light. So they thought if I just keep hitting it with brighter and brighter light, I'll get more and more electricity out. That seems to make sense. But it wasn't the important thing to actually get the electrons to eject. So according to classical wave theory, a wave's energy depends on its intensity, which depends on its amplitude, not its frequency. And then enter Albert Einstein, who was able to resolve the paradox by incorporating Planck's work into his view of particles as a light, his particle theory of light. He actually won the Nobel Prize for that. A lot of people think Albert Einstein won the Nobel Prize for something different, but it was actually for this photoelectric effect that he was working on. So in order for this to work, though, and we've been talking about how light behaves as waves, light can't be a wave here. It actually has to be a particle. So we go from the idea with Isaac Newton of light being a particle to the work of Maxwell and Planck and others, where they're saying, no, this behaves as a wave. And then with Albert Einstein, we're now going back to the notion that light has to behave like a particle. This leads to this duality that light does both. So if we have these equations now that the energy is going to be equal to Planck's constant times the frequency, we can substitute in our idea that frequency is equal to the speed of light divided by lambda, and we now have a equation that's going to relate energy to wavelength as well. So, what is the photoelectric effect? So, electrons are injected when they're hit by photons having sufficient energy. The greater the frequency, the greater the kinetic energy imparted to the escaping electrons by the collision. Somehow, at a fundamental level, still not fully understood, light is both like a wave-like and particle-like. This is known as the wave-particle duality. So let's picture that for a second. So at 700 nanometers, we don't get any electrons off. All of a sudden, we hit some critical value, somewhere around 550 nanometers, and we start to see these electrons getting shot off, and they have their own velocity. And we can measure that. So let's say that at 550, we get 2.96 times 10 to the 5 meters per second electrons shooting off here. If we go even lower wavelength, higher frequency, higher energy, we see that these electrons start to shoot off quite a bit faster, 6.22 times 10 to the 5 meters per second. So let's do a little example where we're looking to calculate the energy from the wavelength. So when we see light from a neon sign, we are observing radiation from excited neon atoms. If this radiation has a wavelength of 640 nanometers, what is the energy of the photon emitted? All right, so we're going to use that equation we had before, where energy is equal to Planck's constant times the speed of light divided by lambda. We're going to remember that we need to convert our wavelength from nanometers to meters. We cancel all of our units, we get joules, and we see that this light has an energy of 3.10 times 10 to the negative 19 joules. So one thing to point out here is that we get this energy value in joules, and it was kind of tricky the way they asked the question. So they said, what is the energy of the photon emitted, right? So what we're really calculating here is that this is the energy per photon. And some other times when they're going to ask these questions, if you look in the homework, sometimes they're going to ask, what is the energy per photon? And they may even start to ask you, what is the energy of multiple photons? In which point you need to realize that that would just be some multiple of this energy. So there's a good example of this in the homework problems. It's just something to pay attention to, that It really depends on how they ask the question. So continuous spectra. So the scientists in the late 19th century, they were also struggling with something else. They were looking at light that was emitted from atoms and molecules. And they noticed that when solids, liquids, or condensed gases, gases at high pressure, relatively low temperatures and stuff, are heated sufficiently, they radiate excess energy as light. Okay? And when they were looking at this, they saw that this produced a continuous spectrum, so that there were photons of many different frequencies that were in a whole continuum. However, when they started to look at gases at low pressures, they started to see what they call line spectra, these discrete spectrums where only light of specific frequencies were emitted. And we can kind of picture that with like the neon signs. So you put different types of gases in these glass tubes, and then you go ahead and heat them and apply electricity to them, and they automatically glow with a specific color that is associated to a specific frequency that they're emitting. Each emission line consists of a single wavelength of light. This implies that the light emitted by a gas consists of a set of discrete energies. That's that quantization again. The origin of discrete spectra in atoms and molecules was extremely puzzling. Where is this coming from, right? Because it really didn't fit with their classic electromagnetic theory. Here we can picture those line spectra that are happening. On the top we have a continuous spectrum, and then down here you can see that if you did sodium, you'd only get these frequencies, and if you did hydrogen, you'd only get these ones. So what's happening is that there is quantization here, okay? If the mechanism that is causing photons to be emitted here is that photon is absorbed by hydrogen, right? And then that causes an electron to go to a higher state, all right? And then the electron falls back down. It's going to emit a photon that has a specific thing here. So if all the electrons in hydrogen could have any value, any energy state, then you would get the continuous. But if there were only some permissible energy states for the electrons in the hydrogen, then you wind up getting these discrete states. That again is an example of the quantization, and we're going to jump into that now with some of the theory behind it. In 1885, Johann Balmer was able to derive an empirical equation. So empirical meaning he looked at data and he found an equation that was going to fit that data. He didn't really have any good theory behind why it was true. The equation related the 4 visible wavelengths of light emitted by hydrogen to whole integers. So here he's able to say, well, the wavelengths that we're going to get out, or 1 over the wavelength that we're going to get out, is going to fit this. Okay, so I have some k value here, and if I start pumping in integers of 3, 4, 5, and 6, I'm going to get out the proper wavelengths that I see. Other discrete lines for hydrogen atoms were found in the UV and IR regions, and it wasn't really, and so this didn't really account for that. But a guy named Rydberg comes along, looks at Balmer's work, and he's able to develop an empirical formula that predicts all of the emission lines, where he now has his constant that he pumps in here, and using his constant, he's able to have 2 different n values, where both of these n values are integers. One is always less than n1 is always less than n2, and we are able to now get all of the possible predicted hydrogen emission lines.